Hello, fans of geometric methods. Welcome back. We have a tutorial on form finding of three-dimensional, stable, and statically determinate spatial structures. The techniques are, I think, infinitely malleable here, but I want to preface this by saying you don't need to do any of this. If you are Zaha Hadid or Pierluigi Nervi or Calatrava or whatever, you could do this, right? Myron could do this maybe, but mere mortals cannot do this without some help. So, what am I talking about? I'm talking about stabilizing nodes, floating nodes in three-dimensional space. Not the nodes on the ground, but the ones floating here, like PQRSTU here. You could do this in a very prosaic manner, sequentially stabilizing them as we do at Cal Poly. Some look clean and elegant, others look a little random, whatever you want, that's fine. And I showed this in the first book. This is figure 7.25, using the stabilization method of spheres as mechanism. So what do I mean here? The This is in the new book. This is in architectural structures. This is figure 422. So it's really easy to see. Hold a pencil at its sharp lead point with your fingers. The eraser of the pencil moves in a spherical mechanism. That's the instability. It's a spherical mechanism. Now hold two pencils on their sharp lead points. P2 and P3 are the lead points. Yet join the erasers of the two pencils. That instability is the intersection of two spheres, which is always a circle. So that instability is a circular mechanism. However, if you have 3 points that are enveloped by 3 spheres, those 3 spheres intersect to a final crown, or it's easier to see the intersection of the circle and the sphere. That's the final crown. Now there's one below the ground also. We ignore that. So let's just look at this one as final crown. That is unambiguously stable, unconditionally stable. If I go from P1 to final crown, P2 to final crown, and P3 to final crown. And then you could build off of that with another set of spheres. Like here's a sphere on crown 1 and points 5 and 6 on the grounds. This is figure 423 in the book. And yes, that works, but it's not rich. It's not fruitful compared to what you're going to see here. A new workflow creates structures like this. Now, there's nothing special about this. It's just demonstrating the workflow. Here's a couple of things I would suggest. One is use symmetry, especially when you're starting out. It's going to make things a lot cleaner for you to see and to follow. Start with a simple polygon on the base. It can be a square. It can be a pentagon. It can be a hexagon, whatever you want. I'm starting with a square. And then put spheres on the corners of that base polygon. I suggest having 4 different radii for those spheres. Get the circles between the intersections of the spheres, and here's the key point in bullet D. The intersections of those circles are what generates these points, shown very, very simply in the book here and very, very richly in this video. So here we go. There's the base plane. I'm using meters as most of the world does. It's a 25 meter square, A, B, C, and D. B is malleable in that you can move it around. A is anchored to the origin, and the whole polygon distorts with that node. That's why I changed the color of it. 4 different spheres. Please label them as sphere A, sphere B, sphere C, etc., just to keep everything straight in your script. Get the circles, which is circle AB is the intersection of sphere A and sphere B. Obviously, they're not intersecting here. I'm just showing it to you. Inflate the radii such that there is a circle here That's circle AB. The next one is BC, etc., etc. And then keep inflating it until those circles start to intertwine. And here we get that hyperbolic paraboloid, EFGH, which I really like. You could see it here. EFGH is that hyperbolic paraboloid, but we'll exploit this much more here. Please do this. Take a snip of the radii when you're reasonably happy with the form. Notice the 25-meter footprint that we started with. So this is going to be a big structure, a big spatial structure. The reason why I think this is important is that you are literally just playing around with these radii. This is the play part of discipline and play. But once you have something reasonable, take a snapshot of it, because you will rapidly get tangled up, and you'll see what I mean in a second. The next steps are completely up to you, as are these steps. I mean, completely up to you. These are not stable points. They are just points in space. What did I do with them? I used symmetry. So I made a plane that bisects my original square. I reflected those points, E, F, G, and H, over to the other side of the polygon. And then I did one more reflection in the other direction, so I have a whole bunch of points in 3D space. Now, excuse me, now this is what I suggest doing. Other people can maybe do it differently. But here's what I did. I made the hint of the hyperbolic paraboloids, the 4 of them. Here it is in plan view. There's the footprint. There's that malleable point B. And now I suggest the following. Make sure you stabilize everything before you start playing with the parameters. Let me repeat. You must stabilize each point individually with 3 struts that are anchored to stable ground or to other stable points. That's the Cal Poly way of doing it. That's the Cal Poly way of doing it. Now here, you may think I'm cheating and I'm not 100% satisfied with what I did. I dropped verticals from EH, that outer ring. I'm not adding new points. These are not floating points. They are down on the ground. In fact, I didn't even draw them. I just showed you the columns intersecting the ground plane. So I still have 2, 4, 6, 8 floating, 16 points. 8 on the inner perimeter, 8 on the outer. So I have 16 floating points, which is 16 times 3 sticks. But I think doing it sequentially like this and maybe color coding it like I did, if you're color sensitive here, the sticks going into the space are black and the columns are purple. Then I'm not really happy here. I made X's on the perimeter, the outside perimeter, going to the initial points. I guess I could have added more ground points like I did over here, but I kind of thought, let's make X's. Myron did this at the Coliseum, the Golden State Warriors Coliseum, right, in Oakland. So I went Myron here, but you could see what's happening. Now, this is not stable, but I'm getting there. And the outer perimeter points are stable. Here I have the purple, and I have a red, and they are not coplanar. All 3 sticks are not coplanar. Okay, and that's the key. And I think that's true. I hope that's true, otherwise I'll be embarrassed. Okay, then I need to sequentially start stabilizing those 8 floating points on the inside. I decided just to X them out again, and I used a different color here. I'm going down to the ground to the original base points, a couple of different views. It's a little tricky to see sometimes in GeoGebra. And then I added green struts to finalize the stability. So now I have 16 points, 16 times 3 sticks. I think it's unconditionally stable, but it's not really architecture because everybody's leaning in, and I just could not resist this. So I don't know if it's questionable. I decided to put a line through the centroid of the original polygon and put a dot on that, and I want a dome or something. Like, it's starting to look like a church or a mosque or a synagogue or some kind of sacred space here. I want a dome over this, which adds a point, which makes it indeterminate. I know, but I could remove them later if I want. So that's exactly what I did. I passed an arc from edge to edge. You could see it here in plan view. And boy, does it look. I like it. I like it. 3D printing. I'm still not happy about this X on the outside, but in general, I'm very happy with this form. So 3D print it, play around with it once you're happy with the designs, okay? Notice that this X is not a floating node. There's no node here. The nodes are clearly marked in the 3D printed model. All right, now we go nuts. And literally, an infinite number of forms can be found here. All I'm doing is changing the radius. I'm not even changing the height of the crown point, nor am I changing the size of the 25-meter square. Some are irrational and sculptural. Some are beautiful. All of them are surprising, I think. So let's just take a peek at how that looks in GeoGebra, just so you see what I'm talking about. I could move the floating point, of course. That's easy. Let's leave it up for now. But I could start changing the radii, and you could see what happens immediately. Like, lots of different things change so fast that you can't even keep track of it, right? So that's what I mean by taking a snapshot of something that looks good. Actually, I like that one too. But, crazy, crazy things happen, right? And are they stable? Let's not talk about this point out here because that was my flourish, my superfluous flourish. But, boy, oh boy, I find this to be dizzying and mesmerizing at the same time. And there's really no limit at all to what you could do. And it's certainly tricky to see things in one shot. So you got to spin it around and move it. This one is nice because the X's sort of form walls of my space, right? I really like this one. I might have to save this one. So if you like something, just save it as print demo 2, because I kind of like that one. And then go back to your PowerPoint. So print them up when you're done. Here's another 3D print of something that looks promising, right? And here's again what I said earlier. If I was Pierluigi Nervi or Musumeci or Zaha or whatever, a brilliant designer, I might not need this technique. Maybe they could have come up with this. But now, using this workflow, I can, and I did, come up with this, and I can come up with an infinite number of other alternate forms. Here's one where it might be hanging, which I really like too, where that crown point drops down. Another 3D print. Fortunately, the 3D printers are very cheap, and we have a whole bunch of them here at Polyshells LLC headquarters. Okay, well, I hope you loved the video. Please ask questions and start designing.